Okay, any questions before we start? We have 3 sessions left until the end of the term. So with these 3 sessions, we're going to be covering 2 chapters, linear regression, simple linear regression, and then multiple linear regression. Okay, so let's get on with this topic for today, which is the focus will be a simple linear regression. So do you see this PowerPoint slide on your screen I'm sharing?
Yes.
Okay, good. I'm not going to go through all of the slides here, but I'm just going to pick maybe a couple or three of them to kind of give you an overview of what we will be expecting, or at least what we will be going through today and then in the next session. So as I mentioned at the last meeting, as far as the regression chapters are concerned, we'll spend more time talking about chapter 13 because this is where the important concepts surrounding regression analysis are introduced. Okay, and then for multiple linear regression, that probably will deserve maybe 1 session because most of the things that we will be talking about in that chapter will have been covered in chapter 13. Okay, so to start, again, let's look at this slide here, which just a repeat of what we've seen in the ANOVA and the chi-square chapters, where we talked about procedures for determining correlation between variables. That is, if we are interested in determining if a particular variable of interest, which we call the dependent variable, using a predictor variable, again, we look at the classification of the variables such that once we're able to classify them according to these 2 categories, we're able to pinpoint the appropriate procedure. So for the next 2 chapters, at least for this chapter, we will be focusing on regression and correlation analysis. So you will note that the response variable is something that is measured, okay? Something that is quantitative. And for the independent variable, that also is one that is measured, so both quantitative, okay? So if you have data and you are asked to perform independence or correlation analysis, and if both X and Y are quantitative, then the appropriate test for that would be the regression and correlation analysis, okay? So as far as this chapter goes, here are the major learning objectives. We've already talked about, this particular learning objective. In fact, we've been going over this learning objective since the ANOVA chapter. Okay, but so we'll still, for every problem that we will solve in this chapter and the next chapter, we'll still identify the response variable as well as the independent variable or independent variables. And then we will calculate, test. This, when I say test, we're going to conduct hypothesis tests once again and interpret the relationship between the 2 variables using the correlation coefficient. Okay. Now the symbol that we will be using for the correlation coefficient is R. Okay, and we'll define this later on, what a correlation coefficient is, what kind of values would we want to expect as a way of measuring strength of correlation between X and Y, between the independent variable and the response variable. And then we will apply regression analysis to estimate the linear relationship between 2 variables. So for here, we will be using Excel to perform the regression analysis. When I say perform regression analysis, what I mean by that is we will be using Excel's data analysis or the interactive Excel template to do the calculation for us. Okay? And then once we have applied regression analysis to estimate the relationship between the two variables, we will try to make sense of the numbers that we see in the regression output. We will evaluate the significance of the slope. Slope of the regression equation pertains to, just kind of give you a heads up, the linear relationship that we will be investigating in chapter 13 will be, in this form. All right, so you're all familiar with this equation, right? Based on your, what you learned in algebra, either from high school or in college, that we're talking about that if we graph, say, x and y, that based on, a sample pair, n pairs of observation, if x and y are linearly correlated, then the graph or the scatter plot of x and y will look something like this. I mean, the dots representing the observations. And then you will note, hopefully, that when you graph x and y, you'll see something of a relationship between x and y, and that we can say, hey, you know what I'm seeing here is maybe a line that would best explain this relationship between x and y. All right. So in this model, we'll use a y hat. Y hat would be the point estimate of the actual linear equation. In as much as x bar is a point estimate of mu, this equation here is simply a point estimate of the actual model, as denoted by this. All right. So in the models, this is the, let's see, that is the actual slope of the relationship between x and y, which we're trying to estimate. And when you take a sample size n and then run a regression on that sample, you obtain what is known as estimate of the slope of the actual equation. All right, so that's what this learning objective number 5 is, evaluating the slope of the regression equation, whether the slope is positive or whether the slope is negative, or whether there is no correlation between x and y, meaning the slope of the equation, actual equation, is equal to 0. Here, we're saying that the relationship between x and y is direct, meaning there is a positive correlation between x and y. The translation of that is that as x increases, or as x moves to one direction, y will follow in the same direction. All right. In this third example here, this is where the slope of the actual line is less than 0. So in this case, we're saying that there is an inverse or indirect relationship between x and y. That is, y will take the opposite direction of x. Okay? So that would be the learning objective number 5. And then learning objective number 6 is really using the resulting regression equation for predicting the value of y. All right, and that's really the reason why we develop models, so that we can estimate the actual value of y, or we can also use the equation to estimate the actual slope of the model. All right, so let me shift here. Do you see this Excel sheet? All right. By the way, this is this particular file is in Moodle now. I uploaded this file this morning. So if you download it, you should be able to see, these different tabs. All right. So that particular learning objective number 6, is in this steps in regression analysis. That really talks about over here, okay, using the model for estimation. So as I said, this is the goal of when you develop regression and correlation analysis. You do that because you want to do this kind of estimation. Okay, I'll get into more detail about these two, the estimating the actual slope of the equation and estimating the actual value of the response variable later on. But before you get to this, to the estimation, using the model for estimation, what we actually do is once we have generated or estimated the linear relationship between x and y, we will subject that model to a series of tests. Okay? When I say series of tests, these tests are listed here. All right? The test will include estimating the appropriateness of the model, meaning the appropriateness test will answer the question, so if you have data that shows something like this, and you try to fit a line through that, the question is, does the linear model y hat is equal to a plus bx is a good representation of the relationship between x and y? Okay, that's the appropriateness. Once a model is determined to be appropriate, meaning once we have determined this to be an appropriate representation of the relationship between x and y, then we will test that model for significance. Okay, well, actually, let me reverse this. We'll do this first. We'll make this A, and then we will make this B. Okay, we'll test the model for significance first, and then we will test the model for appropriateness, which is over here. All right. So are we clear so far in terms of setting the foundation for what we are about to discuss this afternoon? We good?
Yes.
All right. All right. Thank you. So let's look at some examples here. Regression analysis, especially this part here, right? The bottom part. So regression analysis will help us answer questions like this one here. It says, does the amount health tech spends per month on training? And so you see there that here's your first variable, amount spent per month on training. Affect. It's another term for, is there a relationship between this variable and the monthly sales, right? So we see two variables. Which one is the response variable? Which one is the variable of interest? Well, in this case, we're interested in looking at monthly sales as it is affected by the amount spent on training per month. So this is your predictor variable. Okay? Both of which are quantitative. So to answer this kind of question, what you will need to do is to collect XY pairs of observations and then run regression on that sample data. Next question, is the number of square feet in a home related to, so you were using, they're using a different word instead of affecting, using the word related to the cost of heat to heat the home in the month of January. Okay, both of these variables are quantitative. The variable of interest is the cost of heating the home, and we're going to use the size of the home as measured in square feet as the predictor variable. So once again, because of these two variables are quantitative, regression and correlation analysis would be the appropriate test. And then a third question is, does the number of hours students study for an exam influence exam score? Okay, so in these three examples, you see words such as affect, related to, or influence as terms that are synonymous with or interchangeable to this word. Are they correlated? All right, or are they dependent? So this is X and this is Y. Both X and Y are quantitative. So therefore, the appropriate test would be the regression and correlation analysis. All right, so let's look at things that we need to understand now as far as when we look at problems, typical questions that we ask, okay, or at least I will be asking. I just want to make sure that we understand, we are able to answer these questions, because if we are able to do that, then the analysis becomes easier, and then you're able to interpret the data correctly. All right, so we've already talked about this number one here, right? What is the response variable? What is its classification? So in those three research question examples we did, we pretty much answered 1 and 2, including number 3, right? So number 4 is when it says, what is the regression equation? What this question is really asking is that we will be, based on data, so based on sample, we are going to generate the values for A, known as the y-intercept, and the value for B, known as the slope of the line. Okay, so let me draw one more example. Well, let's just redraw that. So let's say that I collected n, say my sample size of 20 XY pairs of observation. And when I plotted these 20 pairs of observations, I observed this scatter plot. Okay, so clearly the relationship between X and Y in this example is fairly linear. All right, so that your book will show you the way to compute the y-intercept and the slope, using a formula. We're not going to deal with that. We're going to have Excel compute these numbers for us, okay? So using what is known as the least squares criterion. So when you run a regression on Excel or any other statistical software, what that will do is it will generate values for the slope, the y-intercept, which is defined as, let me just get rid of this thing here. So A is known as the y-intercept, all right, y-intercept, and then B is known as the slope. Okay, so what is the y-intercept? Well, the y-intercept is the number where, on this y-axis, that is where the line crosses the y-axis. So intercept is where the line crosses the y-axis. Excuse me, when x is equal to 0. Okay, so that would be this point here. The slope is defined as, well, this is something that you may have heard maybe in your economics class or maybe algebra class. The slope is defined as, in a technical way, is known as the rise over run. The rise over run, meaning, by how many units does y increase when x is increased by 1 unit. Okay, so let me use another definition of the slope. So the slope is defined as the amount of change, in y for every, and here's the key here, okay? Every unit change in x. Now, at this point, I'm still using a somewhat generic term, such as change. I'm not using increase or decrease, because sometimes, if you have a relationship like this, when x increases, y decreases, okay? But when you have a relationship between x and y that is direct, the change in x, meaning when you increase x, y will also increase. Okay, so in this, when you are later on, when we look at problem solving, we will be using the more appropriate descriptor here, depending on what we see in terms of the relationship between x and y. Okay, are we clear so far? Now, when we perform regression and correlation analysis, not only are we able to estimate the value of the y-intercept and the slope, but we can go beyond simply developing this model. We can answer questions like, so other questions that we might be interested. How strong is the correlation between x and y? Okay. In simple linear regression, we will be able to answer or put a number to this word strong. You know, there is a number that measures the strength of correlation between X and Y. What is that number? Well, that number is known as, this is known as the R value, or the symbol for it is R, which is known as the correlation coefficient. Okay? The correlation coefficient is a value between -1. So I'm just going to do this. So R is between -1 and +1. So what do we consider as strong correlation between X and Y? When the R value is close to 0, okay, close to 0, then this means that there is no correlation between X and Y. All right? When the R value, okay, when R is equal to -1, erase this extraneous character there, then this means that X and Y are perfectly linearly and inversely correlated. Okay? And then when R is equal to 1 plus 1, then we can say that X and Y are perfectly linearly and directly correlated. Okay, so I've given you sort of extreme values on the negative side, and then extreme values on the plus side, and then our value in the middle of these two. So if we represented these three extreme values, these values in terms of a graph, when you graph X and Y, let's say that here's your scatter plot. All right, this is a representation of this kind. Okay, meaning there's no correlation between X and Y. For the second example, when R is exactly equal to -1, that means that when you plot the observed values, the sample data, okay, represented by these little dots, that the line will go through those dots, exactly on those dots, okay, such that give me the value of a given X, I can tell you exactly what Y will be. All right. The third example is where, that would be this, okay, +1. Let's see if I can reverse this. Okay, so that now we're consistent with the representation of perfectly, linearly, and directly correlated X and Y. This here is where, when the R is -1, that means that, you know, the observed values represented by these little dots are in perfect alignment, such that if you generated a regression equation based on these observed values, the line will go through exactly those dots. So this will show a -1 correlation. Okay? As the observed values disperse around, so let's say that you have another set of data representing X and Y. Note now that the observed values are a little bit dispersed around the line. Okay? This kind of plot will generate a value, an R value that is not exactly equal to, you know, -1, but it will be close to -1. Maybe it'll be 0.8 or 0.9. Okay? And for this third example here, maybe you have plots that look something like this. Okay, and then when you generate the correlation coefficient, then this will have an R value that is close to +1. Okay? I think I want, let me see if there's a, okay. This is a slide that puts words into the values of R. So maybe you would want to refer to this slide when you are interpreting an R value or a correlation coefficient value on an output. So if you get a value that is between, say, -0.5 and -1, then we can characterize that relationship as strong negative correlation. Okay? Around 0.5, you'll say that it's a moderate negative correlation. And then between 0.5 and 0, you'll say that there's a weak correlation. All right, now again, the R value will get closer to 0 or going this way or this way, depending on the dispersion of the observed values around the regression line. Okay, we clear so far? Now, the sign that you see here and here, the sign is not an indicator of the strength, not an indicator of strength of correlation between X and Y. Okay? The sign of the coefficient, a correlation coefficient, simply tells us whether the relationship is inverse or is positive or direct. Okay? The strength of correlation is measured in terms of the value of R, how close it is to either -1 or +1. Okay, we clear so far? All right. Another important number that will answer this question. How strong or how much of the variation in Y can be explained by X? Okay. So in here, the question is how much of the variation in Y can be explained by x. This question can be answered by the r squared. I'm just going to type this value. Okay, symbolically, r squared is depicted this way. Okay. Note that the r squared value is simply the square of whatever number you get here. So if you get an r value that is negative, and if you square that, it becomes positive, right? So as far as the r squared value is concerned, r squared will range from 0 to 100%. Okay, now note, well, I'll define this first and then I'll tell you about the note. So the r squared value measures the percent of variation in y as explained by x. Okay? There's the key there. Percent of variation in y as explained by x. Now, the note I was going to say earlier is that in Excel, Excel reports r squared as a ratio, meaning r in Excel is between 0 and 1. Okay. Now we note that if you're given a ratio, you can easily convert that into percent by, if you're doing it by hand, multiplying it by 100, or if you are using Excel, you can use the percent format to convert a ratio into percent. All right. Now let's go back to these three examples. Here, the r squared value for this example, r squared will be approximately equal to 0, meaning the variable x does not have anything to do with explaining the variation in y. Okay? For the second example, here the r squared value will be equal to 1, or we can say 100%. And then for this example over here, r squared will also be equal to 1, or we can say that the 100% of the variation in y can be explained by x. Okay, x is a perfect predictor for y, either in this case or in that case. But as the observed values disperse around the regression line, here the r squared value will be probably, maybe 0.9 or maybe 90%. Okay, here, same thing. The r squared value will probably be around 0.9 or 90%. We don't have to compute the r and the r squared value by hand because Excel will generate those for us. Okay, so are we clear so far? Okay, good, because I've gone through at this in the steps here. We've answered, we've talked about the answer to this question. How strong is the correlation between X and Y? Use the number, then interpret the value. So in interpreting the value, I would point you to this slide so that you can assign descriptive term to the correlation coefficient value that is generated by Excel. Okay, maybe I should copy this page here. And then paste that onto the this file. And maybe over here. Oh, I already have that. I didn't have to copy that. Okay. Okay. And then we answered number 6. We talked about answering this question, how much variation in response variable can be explained by the independent variable. And we said that this would be the R squared value. Okay, are we good so far? Now, maybe it's a good time at this point to look at an example, and then we'll take a break. Now, let's take a look at this example here. A suburban hotel derives its gross income from its hotel and restaurant operations. The owners are interested in the relationship between the number of rooms occupied. So here's what they're saying. They're interested in the relationship between the number of rooms occupied on a nightly basis and the revenue per day in the restaurant. Okay, so we are talking about 2 variables. And what are these 2 variables? Number of rooms occupied and revenue per day in the restaurant. Which of these 2 is the variable of interest? Well, they will be using, they want to know using the number of rooms occupied in the hotel, how much does that translate in terms of the revenue per day in the restaurant? So if we go down to the part here, where we again answer the questions related to, what is the response variable? We'll say that this is the daily sales of the restaurant. Okay, and this is quantitative. And as far as the independent variable is concerned, this would be the number of rooms occupied in the hotel. And this is also quantitative. So question 3, what is the appropriate procedure for testing independence? Well, both are quantitative, X and Y are. It is regression and correlation analysis. Okay. Now, specifically, which kind of regression and correlation analysis? Well, here we will be saying simple regression, simple regression analysis as compared to multiple regression analysis. Okay, so what's the difference between a simple regression and multiple regression? In simple regression is used when Y is quantitative and 1x. We're only using one predictor variable, and x is also quantitative. Whereas multiple regression is used when y is also quantitative and we have at least one x. All right, and the x can be a combination of quantitative or qualitative variables. Well, again, look at these quantitative and qualitative variables in the next session, or 2 sessions from today. Okay? And then 4, what is the regression equation? Meaning this one really is asking us to compute the values for the coefficient, asking us to compute the value of A and compute the value of B given a particular data set. Okay? So let's do that for number 4 now. Now, before you can do number 4, let's say before you compute a regression equation for a simple regression model, it is a good idea to first generate what is known as an XY scatter plot. Okay? Essentially, we're saying, hey, you know what? If you have these XY pairs of data, let's develop a plot, something like this, where each individual pair of observations is plotted on the XY graph. Okay, so that the purpose of developing an XY scatter plot is to just give you a visual representation of the potential relationship between X and Y. Okay, so visual representation of the possible relationship or association between X and Y. Okay, I'm going to stress on this word visual representation. All right, so let's generate the scatter plot. When you generate a scatter plot, you would want the independent or the predictor variable in the first column, and then the response variable in the next column. Okay, so let's see if it generates a kind of a, so in anticipation of the graph, if I graph this correctly, here's the graph that I would expect. I would expect to see the variable occupied, this is the number of rooms occupied, on the horizontal axis, and the income by the restaurant on the vertical axis. Okay, again, you want the predictor variable on the horizontal axis, and then the response variable on the vertical axis. Okay, so let's graph these two, highlighting columns, these two columns. I've included the variable labels. We will select insert, and then we will select, and be careful here because there are a lot of, you can see the line chart. What we want to use is this, it says insert scatter XY chart. Select that, and then select this first option. Okay? So here's your rough plot of the data set. I'm just going to cover that. So is it consistent with what I anticipated the graph to be? That is, I want the number of rooms occupied on the horizontal axis. That's this. And then the revenue on the y-axis over here. Now, tip, or at least something that you would also want to know when you are presenting graphical information, whether it's in a class or if you are doing maybe a report. Make sure that your graph or bar chart or whatever visual image you are presenting, that it is properly labeled. Meaning, you know, if you don't have to explain what the graph is, the person will know exactly what the variable on the horizontal axis is and what the variable on the vertical axis is. So as it stands now, you know, we can't tell unless, you know, you read the problem. So I would encourage you to, every time you create an XY chart, make the chart, label it as completely as you can. All right, maybe starting with the title over here. And then you can create a y-axis label or an x-axis label. So Excel will give you various options for graphs. See, as I click, you know, these options here, the layout or the design, note that it changes. What I would want is maybe using this quick layout. And under the quick layout, you can have these different options. So let's select this first one. All right. So the first option allows you to create an x-axis title. So we will just edit this to say daily revenue of the restaurant. And then the x-axis title, number of hotel rooms occupied. And you can change the title to make it more descriptive. So you can say this is number of rooms occupied versus daily revenue of the restaurant. And then you can change the font size to make your graph a little bit more appealing. Okay. As far as coloring the background or using their font colors, it's up to you. But the point here is that when you are presenting a scatter plot, you want it to stand alone, that anybody who's looking at the scatter plot will understand what the variables are in the plot. Good so far? All right. Now, what is it that you observe in, in this relationship between these two variables? Looks like there's probably some correlation here. There's a little bit of a pattern there. So what is that pattern? Maybe we can check and see if we can have a line representing this relationship. All right. Excel will allow you to superimpose a model onto your scatter plot. So I just, I click on any, inside of the graph. All right, and then right click. And one of the options there is this, it says add trend line. Okay, this will allow you to superimpose any of these trend line options. You see that? Now, the default in Excel is that it picks the linear model. So you see this dash kind of like light blue line there? That's the linear option. And you can select exponential. You don't see much there, right? Logarithmic, there's a little bit curvature there. Or polynomial, okay, second order, meaning you have x and x squared. Or third order polynomial, you have x, x squared, x cubed. But look what's happening to the shape of the, what's superimposed on the graph. Now, for now, let's investigate the linear model, okay? Because that's what chapter 13 is about. Simple linear model. For this line, we said that we want to compute the y-intercept and compute the slope. All right, Excel can do that easily for us. So while you are still on this format trend line, you select this option that says display equation on chart. Okay, note that as I selected this option, observe what happens on the graph. All right, so here you go. The equation was superimposed. And the way that Excel will express the equation is a little bit, reversed compared to how we wrote it over here. Excel uses the algebraic symbolism like this, mx, something like this. But the interpretation of A, which is the y-intercept, and M, which is the slope, the interpretation of these two numbers is the same. Okay? All right. Let me go back here, the trend line. So we ask Excel to display the equation on the chart. We can also ask Excel to display the R-squared value, right over here. And maybe that's it. So here's your, let me move this down closer to the questions. Okay. So as far as the question, how strong is the correlation between X and Y. It says use a number, then interpret. So the correlation, or R, is equal to, the graph will not give you the R, but you see the R squared value, right? So the R is actually the square root of R squared. So I'm just typing this out, which is equal to, we're now going to compute the R is square root of 0.1789, 0.1789, and there you go. Okay, so we have just computed the correlation coefficient as 0.42297. What is its interpretation? All right, now the sign of the slope here is plus. Okay, why did I say plus? Why not negative? Well, if you look at the, this line here, let's make that thicker so you can see. So note that y increases as x increases. So we'll say that the relationship between x and y is direct, or also you can say positive. So as far as the interpretation of the 0.4297, what kind of word would we describe the strength of the correlation?
Moderate.
Moderate, okay. So looking at the, over here, so it's around a moderate correlation. Okay, so we'll say that moderate correlation between x and y. Are we good so far? Okay. How about 6? It says how much variation in the response variable can be explained by the independent variable. So here we'll just say the R squared value. And the R squared value is 0.1789, okay, which we obtained from over here. And I said that, we would want to express this in a percent. So we can just use the percent format in Excel to convert that into this number. Okay, so what is the interpretation of this number? All right, so we will say that the number of occupied rooms in the hotel explains about 17, well, just run this up, about 18% of the variation in the revenue of the restaurant. What happens to the, 82%? Well, that 82% is what we call as the unexplained variation. Maybe there are other variables that could add to the, this number here. But as far as the number of occupied rooms in the hotel, it only explains about 18% of the variation in sales. Good so far? So continuing with this problem, we're going through the different steps in regression analysis, right? So the next step, once you have generated the equation, we will subject that equation to a series of tests. And these steps are testing the model for significance, and then the next step is testing the model for appropriateness. Okay. Now, one of the there are three tests that one can carry out testing the model for significance. One of the commonly used ones is known as the slope test. All right. So, what is a slope test? Well, the slope test can be represented in a hypothesis this way. It says the null hypothesis says that the actual slope of the model is equal to 0. All right. Now, in this example here, that would be this. If you have a flat line that expresses the relationship between x and y, that would be the null hypothesis, right? The slope is equal to 0, meaning x is not a good predictor for y. The alternate hypothesis says that, so this is h sub 1, the slope is not equal to 0. All right, meaning, if the null hypothesis is rejected, either the slope is great, positive, or the slope is negative. We don't care. What we simply care about is that the slope is a non-zero number, meaning x is a good predictor for y. Now, the interpretation of the null hypothesis is this. The linear model is not significant. Okay, that's the interpretation of the null hypothesis. The interpretation of the alternate hypothesis is that the linear model is significant. We can use the p-value at this point to make such a conclusion. Okay, where do we get the p-value? Now, the p-value can be obtained. So let me copy this. Back here, where's the, over here. So is the slope of the regression equation significantly different from 0? So we express that in this linear model. Let me insert a couple of rows. Okay. Now, based on, we really don't have enough information based on this scatter plot to render a conclusion here. To be able to render a conclusion on this hypothesis, we will have to run what is known as a regression analysis. Okay? So here's how we do it. I'm going to go back here, delete these, clean this up, because I'm going to put the regression output on this side. Okay. Data analysis, and then one of the options there is regression. We click that, and here's the dialog box for the regression analysis. It says input Y range. The input Y range will be from, see, income, I'm going to include income, the label, scroll down all the way to 1426. Next, we declare the input X range, which would be from L2 down to L27. Make sure you select this option here, especially when you include the column labels, which I did in my case. Output, where do you want the output to start? So I'm going to change this from H4. I'm going to say, I'm going to put the output in O3. Okay, so that will be the upper leftmost corner of the output. And let's include this too, residual plots and normal probability plots, because we will be using this later on when we try to answer the question of, this appropriateness. Okay. And click OK. All right, so do you see this in gray area? That is the regression output. This provides more complete information than the output produced by this XY scatter plot. Okay, so let's look at the this output. This number here, over here, this was the correlation coefficient. Or R. Nope. This number here is the R squared value, known as the coefficient of determination. Okay, so this is the R square value. Don't worry about the adjusted R squared at this point. Now, how about this ANOVA table? Or how about this output here? Now, recall that down in the graph over here, let me move this up so you can see. I'm going to remove these numbers here. Hopefully this will not affect my plot. Oh, no, it affected my plot. So I need those. All right. You see this number here? That is the 1382. That's the y-intercept. Okay, we labeled that earlier as this is A. The 1.478, this is what we call the slope. All right, so if you were given an output such as this, and you were asked to, fill in the information in this equation, you can pick up A from over here. That's 1381.99 plus 1.478x. Okay, where we define y as the sales of the restaurant, daily sales of restaurant, and then x as the number of rooms occupied. Okay? So we will be using this output to answer the hypothesis testing question over here. Is the slope of the equation significantly different from 0, meaning we're trying to do this, right? We will use, at this point, let's just use the p-value instead of comparing the computed f to the critical f, which you can also do. But when you're reading from the output, it is most convenient to just use the p-value as your decision rule. So reject HO if the p-value is less than alpha. Okay? I don't know if the problem has a significance level stated. Oh, yep, there is. All right, here it is. Point 1. So what is the p-value? Where do we obtain that? We will obtain the p-value from either this number here, oh, no, either this number here or this number here. Okay, they will be the same for simple regression. Okay, so again, the significance of f is the p-value of the test. So the p-value is 0.035. .035. Is that less than the significance level of 0.10? The answer is yes. Therefore, we will conclude to reject HO. All right, and by rejecting the null hypothesis, we're saying that the slope of the equation is not equal to 0, meaning in this case it's positive. All right. Rejecting the null hypothesis, we will conclude that the slope is not equal to 0. Or another translation of this is the model, the linear model, scratch that. The linear model is significant. Okay? So if the linear model is significant, then there's a question here. It says, for each unit change in the independent variable, meaning for each additional room that is occupied in the hotel, by how many units on average is y changing? So let me translate this in terms of the actual variables that we're using in this problem. For every additional room in the hotel that is occupied, by how much is the daily revenue of the restaurant changing? On average. Okay. To answer this question here, that would be the slope. Okay. And the slope of the equation is 1.48. 1.48 what? Well, it's $1.48. Okay? So this is the slope of the equation. Good so far? Recall that in earlier, I said that this is a point estimate of the true slope. Okay, in other words, this $1.48 is simply a point estimate of the true slope, which we don't know. So again, the slope is a point estimate of the true slope, in as much as in the previous topics, like x bar is a point estimate of mu, p, sample proportion, is a point estimate of the true population proportion. So in number 9, question number 9 here says, give the 95% interval estimate of the true change in y for every unit change in x. Meaning, to this 1.48, we add or subtract a margin of error to get the interval estimate. We don't have to compute that number, because in the output over here, you see this, so this is the point estimate of the true slope. In here, you will have that number there. It says lower 95%. And then this would be the upper interval estimate of the true slope. Okay? So let me just write that down so I don't remember, I don't forget. 0.112 and 2.84. So the answer to number 9 over here, the 95% confidence interval for the actual slope is equal to zero, this is in dollars, okay? 0.112, like 12 cents on the low end. On the high end, $2.84. Okay? Are we good so far? All right. So at this point, we have tested the model for significance. The next step is to test the linear model for appropriateness, meaning does the line really fit the data? So they say, does the model, the linear model, fit the data? That's essentially what we're trying to answer when we do a model test, the model for appropriateness. For this, we will be using what is known as the analysis of residuals. Okay? Analysis of residuals. Let me move this down. Okay. So in the analysis of residuals, we make three assumptions that we'll be testing. Assumption number one is that the error terms are normally distributed. Two, that the error terms have constant variance. And three, that the error terms are independent. Okay? Let me explain each one. When we're looking at an error term, okay, so here's your line. Here are the observed values. Okay, here's X, here's Y. The points on this line, any point along that line, is what we call as the Y hat, meaning the fitted Y. Okay, a fitted Y is when you substitute the value of X into the model. Okay, so for every X, you say X is equal to 1. What is the value of Y hat, right? When X is equal to 2, and so on and so forth. So you'll have whatever X value here, maybe say, let's say 12, that points on this line are what we call the fitted Y. The distance between this point here, that's called the observed Y. The distance from each of these observed Y's to the fitted Y, represented by these red lines. So when you have Y minus Y hat, guess if I'm looking at this particular point from that far away, this is known as the error. Okay, also known as the residual. So these assumptions that we're talking about here are the assumptions related to these values. Okay? So the first one says, well, that if you constructed, if you're looking at a particular, say, X value, say over here, the distribution of the error terms in that X value will be bell-shaped, Okay, so this you see this like a orange or yellow. It's the normal distribution is rotated to the right. Okay, so that would be the normal distribution assumption. The second assumption and the third assumption typically go hand in hand. Okay, constant variance says that if you're looking at the error term on this low level here, that the distribution of the error terms there will be about the same as the distribution of, the other error terms across values of x. That's what this constant variance assumption says. How do we test whether these assumptions are satisfied? We'll go back to the residuals. Okay, where are those residuals? I thought I created them. There you go. Okay, now over here, normal probability plot. This tests the assumption of normal distribution. Now this, if you see this to be a fairly, resembles a line, then we will say that the normality assumption is met. Okay. This one, the residual plot, you would want to see this in a more random. This is what you want to see. So if this is random, then we will say that the assumption of constant variance is met. Okay, so since these two assumptions are satisfied, they're both met, then and only then can we conclude that the linear model is appropriate. Okay, now so let's go back to the answer here is yes. Why? Because the assumptions above are all met. Oh, I don't want to move that because we're talking about the above. Now we're out of time here. So in our next session, I will pick up from here because I know that this is probably in what we covered today, probably the most challenging one to understand. So we'll look at this again in the next session, and hopefully we'll have a better understanding of the test for appropriateness. Okay? So if it wasn't clear as far as number 9 is concerned, that's understandable. We've covered quite a bit of ground today, so we'll repeat this again in the next session.
Can you use the template for this kind of problem, or only?
Yes, you can. The template, however, does not do the regression, the residual plots. Yeah,
Oh, I
good
see.
question. We will look at using the template next time to do the analysis. Okay.
All right, sounds good.